Hello everyone. In this session, we will briefly see the working of N-channel JFET. So let us begin with some basic things about junction field effect transistor. It's a unipolar device. That means the current flow is due to the majority carriers. It's a voltage control device. We will see shortly how that VGS controls the drain current ID. And it is a high input resistance device. That means here in a JFET, the gate current is practically zero. So now let us see the 2D structure of N-channel JFET. So over here we can see it consists of P plus region, which is marked in yellow color. Okay, so the two P plus region are electrically connected and form a gate terminal, common gate terminal. Okay, and then we have the N channel is between the two P plus region. Okay, that is the N region over here which forms the channel. So here is my channel, N channel. And in this N channel, the majority carrier electrons flow between the source and the drain terminal. Now, source is the terminal from which the carriers enter the channel from the external circuit, and drain is the terminal where the carriers or the electrons over here leave or are drained from the device. And the gate over here acts as a control terminal. Now, all of these terminals are taken out with the help of a ohmic contact. Fine. And since you have a formation of a PN junction, P plus N junction over here, and below also we have P plus N junction, there is a presence of depletion layer. So this is blue color over region. This is my depletion layer, which is automatically formed whenever we have a PN junction formed in the device. Now this is the 2D structure. Similarly, we will be doing the analysis for 1D structure for N channel MOSFET. So basically, what's the difference from 2D to 1D? As you can see, only the front view we are considering, but it is actually in 2 dimensions. Yeah. So let us concentrate over here. So here also we see in the 1D structure, the 2 gate terminals are there. Okay, are tied together to form a single gate connection. We have a depletion layer marked in blue color, two P plus regions through which the gate terminal is connected. And on the left hand side of the N region, we have the source, and on the right hand side, we have the drain terminal. So this is the simplified structure of N channel JFET, which we are going to analyze. Okay. Now, one more thing. Since the majority carrier electrons are primarily involved in the conduction of this N channel JFET, the JFET is called as a majority carrier device or a unipolar device. Now, let us look into the voltage connections, what voltages are connected externally. So let us see that now. Okay, so as you can see, the two gate terminals are symmetric actually. So we have shown over here two VGS supplies, but actually internally we have only one VGS. Since the structure is symmetric, we have shown it this way. Then we have a source which is supply voltage connected to the drain and the source terminal. So as you can see, all the gate and the drain voltage is measured with respect to source, and the source is connected to the ground. Okay, so since the carriers will flow from source to the drain terminal, as you can see, the conventional current will flow from drain to the source terminal. Fine. So these are my voltage connections for the circuit. Now let us start analyzing the circuit in different cases. So let us see the working. Okay. Yeah. So let us start with the working. So for the first case, we will consider two cases. And for the first case, we will consider that VGS applied voltage is 0. And we are only applying VDS voltage, which is very small. Okay. And over here, this dotted line indicates the charge carrier, which are electrons. Fine. So what really happens in this situation now, when VGS is 0, fine, and we have applied a small potential at the drain terminal with respect to source. So let's say that that voltage is VDS, which is very, very small, around 0.05 volt. So what will happen basically, since we have applied a potential difference between the source and the drain terminal, okay, so the charge carriers will start flowing from the source terminal and they move towards the drain terminal. Fine. So that means we have a small proportional increase in the current with increase in the voltage. So this is the scenario of the graph over here. So in this condition where the gate voltage is 0 and we apply a small drain to source voltage, your current ID increases linearly with VDS. First, very small values of VDS. So over here, the amount of current which is flowing is ID1, and correspondingly the value of VDS is VDS1, which is 0.05. So why the current flow? It's exactly linear over here. We'll see that shortly now. Yeah. So essentially what happens is for very small voltages, the channel act as a resistor. Okay. So what really happens, let me explain you with an example. Here we are considering VD voltage as 3 volt, for example. So let's consider this situation. So what really happens is your entire channel is uniformly distributed now. Okay. So your effective channel resistance varies along the channel length, and that is what is happening. So if effectively it's acting as a resistor. So let's say you have this 5 resistors. So let's say you have applied a 3 volt. So this 3 volt is dropped across the channel in this form. So here let's say all the resistors are same. So according to the voltage division rule, voltage over here near the drain end will be 2.4. At the drain it will be 3. Little bit away from the drain it's 2.4. Then it's 1.8, 1.2, and near the source it will become 0.6, and at the source terminal it will become 0. So we can say that here the channel is acting as a resistor, and the resistivity of the channel is given by the formula rho L by A. Okay, rho is the resistivity, L is the length, and A is the area. Okay, so area between the two depletion layers, that is blue color regions, is my depletion, is my area of the channel. Fine. So that is what is happening. So until my VDS is very, very small, my channel will act as a resistor. Fine. So that explains the situation. Case number 1, where we have a very small drain to source voltage applied, and you have a linear increase in the current, ID1. So here we can say that the drain current increases linearly with the drain to source voltage for very, very small values of VDS voltages. Okay, so let's proceed further. So earlier we have applied a very small value of VDS. Let us slightly increase the value of VDS. Okay, so earlier it was 0.05. Now that voltage has increased to 0.1. So what really happens over here is that as you slowly increase the value of the drain to source voltage, the PN junction between the drain and the gate region over here, it's slightly more reverse bias. Because see, actually what is happening is we are applying a a positive potential to the N region, and here the gate potential is applied to 0, ground. So you're reverse biasing the PN junction near the drain and the gate region, whereas the source region is still connected to ground, and the gate is also connected to the ground. So there is no change in the depletion region at near the source end. But as you can see slightly, the depletion region is extending further for near the gate and the drain region. Okay, we have seen that whenever the PN junction is reverse bias, the depletion region slightly increases. So what is really happening over here is that the area over here near the drain region, it has reduced. As you can see, near the source region it's larger, and near the drain region is slightly constrained. So what is happening is as the drain voltage increases, the gate to channel PN junction becomes reverse bias near the drain end, and due to that the depletion region widens, extending further into the channel. Okay, even though the channel will act as a resistor over here, the effective channel resistance will increase as the depletion region widens. Let me explain it to you with the help of the diagram. Okay, so right now what was the condition? That the area near the drain end was increasing. That means this resistance over here is increasing, and we can say that effectively how it is increasing, because the area near the drain end gate and drain region, it's reducing. So if the area is reducing according to this formula, resistivity of the channel near the drain end is increasing because the area is reducing. Okay, so what will really happen is, so due to the effective channel resistance increasing near the drain end, because the area is reduced near the drain end, so your current will increase, but since the effective channel resistance increases, the slope of this curve will also definitely will be decreasing, as you can see. So there will be an increase in the current. We can say that id, the drain current, increases with the applied voltage vds, but the amount of increase has been reduced, and since the slope has reduced due to the effective channel resistance has increased. Okay, so now we'll continue further. So further, if we applied a vds voltage to, let's say, 0.18 volts, as you can see, oh sorry, so further, if your drain to source voltage has increased further, as you can see, the drain near the PN junction near the drain and the gate region has widened more, reducing to, reducing the area near the drain region. So what will happen? The current will continue to flow. The electrons will be flowing from the source to the drain, but near the drain end, the effective area has reduced. Due to that, what happens? The effective channel resistance has increased further. So ID3 is corresponding to this condition, and VDS3 is the voltage at which. So the current will continue to increase, but with a decreased slope, as you can see. So this is happening because of effective channel resistance increasing. Okay, so your effective channel resistance will now vary across the length of the channel, and what really happens is, when the channel current has to be a constant, so voltage drop through the channel becomes dependent upon the position. So if the drain voltage value is increased further, the following condition might occur. So this condition might occur at, say, a voltage VDS of 0.2 volts. So what is this condition? Uh, since the increase in the drain to source voltage has increased so much that the channel has become pinched off at the drain end. Okay, the channel is almost pinched off at the drain end. So over here, any further increase in VDS will not increase the drain current now. Okay, we can say that the drain voltage VDS at pinch off is VDS sat. Fine. So right now, what will really happen is that at this condition, at the pinch off condition, your current, instead of going to zero, will remain constant. So here is the region. So this region of operation is called as saturation region. We will see in a moment why the current remains constant. So for any voltage, VDS voltage greater than VD sat, so this VDS4 is nothing but VD sat. The transistor is biased in the saturation region, and the drain current is almost independent of VDS. Even if you increase VDS further, the current will remain constant, which is corresponding to ID4. So why really this happens? Let us try to understand that. So at first glance, we expect that the drain current should be going to zero when the channel is pinched off at the drain terminal, but this does not happen. Let us understand why. So let us look into a detailed diagram of N-channel MOSFET under that condition, wherein we have your pinch off condition reached at the drain terminal. Okay, so this is the expanded view of the depletion region in the channel for VDS voltages greater than VDS sat. So the electrons, we observed over here that the N channel and the drain side are now separated by a depletion region of length delta L. So as you can see, now the channel over here has reduced, and earlier it was L. This was the channel, but just wait a second. Yeah. So earlier the channel length was this, and now it has reduced to this delta L, because the electrons from the source have to travel this small area and has to reach the drain region. Okay, so yeah, so on the right hand side we can say we have a voltage VDS at the right hand side of this channel, and towards the, if you move further towards, this is VD sat. Okay, and whenever VD sat is beyond, VDS voltage is beyond VD sat, then only this condition will occur. So let's start. Okay, so please concentrate over here. So the electrons will move to the n channel from the source and are injected into the depletion region, where it is subjected to very powerful electric field. Now see what happens over here. Electric field is given by the formula voltage upon length. Over here the length has reduced from delta L to L to delta L, and your voltage has also increased. Your VDS voltage has increased further. So the voltage is increasing, length is decreasing, so electric field will become very, very powerful in this small depletion region. Okay, because here the PN junction has heavily reverse bias now. Okay, at the condition almost it is touching at the drain end of the channel. So under the influence of this very powerful electric field, electrons which are coming over from the source terminal are swept away towards the drain terminal. Okay, now since delta L is small, the electric field power, the strength is very, very high until it reaches a critical value. So you must have seen this small curve before. This is a graph of electric field versus the drift velocities. So as you can see, until it reaches a critical electric field, your drift velocity of carriers will reach a constant value, and electric field remain constant beyond VDS greater than VDS sat. So over here, the velocity with which the average velocity, the drift velocity is the average velocity of the carriers, will also reach a constant value. This is the reason why your current will saturate. The current will flow steadily. Okay, increased, current will flow at a constant rate. So therefore, because of this concept that electric field has reached a critical value and the drift velocity of the carriers has reached a constant value, hence the current, carriers which are flowing into the source region, from the source region and towards the drain region, what they will do, under the influence of very powerful electric field, their average velocity will reach constant value. Hence the current in this condition will remain constant and will be independent of VDS. We can say that in this condition the device behaves as a constant current source. Okay, and the JFET is fully turned on. Fine. So this is the condition, and this explains why the current remains almost constant once it is reaching a voltage VDS sat value. Okay, hence the current over here remains constant. Okay, now we move forward. So we'll explore the second condition now. So second condition is that the VDS voltage is very, very small, and we are varying the value of VDS voltage is small, 0.05, and we are varying the gate to source voltage. Okay, so here this condition we have already seen before. Fine. For very small value of VDS voltages and for VGS equal to 0, the current will increase linearly with increase in the VDS voltage. Okay, that is no problem over here, right? Now next, if a negative gate voltage VGS equal to minus V1, let's say VGS is minus 2 volt, is applied, the gate to channel PN junction becomes reverse bias. Okay, now this gate to channel PN junction is same at the drain end and at the source end, because at the drain end the voltage is almost constant now, and at the gate terminal we have increased the voltage. Okay, so at both the sides what will happen is the depletion region width will increase, because now the depletion region widens and the n channel becomes narrower, as you can see. Okay, so what we can say, that the area has reduced, correct? So that means that when the channel is becoming narrower, the area is reducing, right? So channel is still acting as a resistor, but since the area is reducing, the channel resistivity will increase. And again, the current will be there, the current will be flowing linearly, but it will be with a reduced slope. So for VGS equal to minus 2 volt, you will again get a linear increase in the current, because we are having a very small increase in the VGS value is going to minus 2, but the VDS condition remains the same, very small. Okay, so for small values of VDS, channel is again acting as a resistor, And but right now the channel resistivity has increased because the area is reduced. Now, if you continue further, a condition will reach where the reverse bias gate to channel depletion region will completely fill the channel region, as you can see. Okay, so let's say when VGS voltage reaches -4 volt, this also is called as a pinch off condition. Whenever VGS voltage has reached a higher negative value, at this point of time, as you can see, both the depletion regions have covered the entire channel. So the depletion region has isolated the source terminal, I mean source side and the drain side. So there is no way any current can flow over here. So we can say on the graph over here, whenever VGS has reached a pinch off condition, that is whenever VGS is equal to minus VP, the current in the channel becomes zero. Since the depletion region isolates the source and the drain, and the drain current at the pinch off is essentially zero. And we can say for all practical purposes, the device has been shut off or turned off whenever VGS becomes equal to minus VP. So in this manner, your drain current in the channel is controlled by gate to source voltage, as you can see. And we can say that the JFET is a normally on device or a depletion mode device because external voltage has to be applied to its gate terminal to turn the JFET off, to turn the device off. Okay, so we will revise what we have done so far. So first we have analyzed the construction of the JFET, find the 2D structure. Then we have seen how to convert it into a 1D structure. Now, one more thing which I want to say in this is because the both the gate terminals are same, so the channel thickness is increasing symmetrically at both the places. Okay, under these conditions. So next we have seen that number one condition, that is varying the value of VDS when VGS is kept at 0 volt. So we have seen that there is a linear increase in current, and then due to the effective channel area reducing, the channel resistance increasing, there is a fall off slope, and this continues further until condition is reached at the drain end. The channel is almost very small, and at this condition, the saturation condition, the drain to source voltage has reached the saturation voltage VGS, VDS sat, and now the current has become independent of the supply voltage VDS. Okay, now it will remain constant throughout, and we have seen that in detail why it happens. Because the electric field has reached the critical value, the average velocity of the carriers has also reached the constant value. So the carriers which are coming out of this small depletion region will be having a constant velocity. Hence, the current remains constant. And we have also seen the second condition, wherein the VDS voltage is very small. So channel is still behaving as a resistor. And as you go on increasing the value of VDS more and more negative, the channel becomes narrower and narrower, and the area is reducing. So the effective the resistance channel resistivity will increase, and there will be a fall off slope in the current. At one condition, the entire channel, both the depletion region will cover each other, and it will isolate the channel, the source and the drain end, and the current will be essentially zero. So this is how the entire JFET N-channel JFET works. Similarly, for a P-channel JFET, both the gate regions will be of N plus, and the channel will be of P channel. Okay, so I think that is all for this session. We have seen the construction and the working of N-channel JFET, and now we can say that it's a voltage control device because it was the gate to source voltage which was controlling the drain current from the source to the drain terminal. Okay, so that is all for this session. Thank you for joining.